So that is we have our inner integral at least. If we look at, for our top view, I need to switch these labels. This is x and this is y. All right, so here we have y equals 0 and y equals 2. So the x-axis is running along this way. So I've taken this view and I've just turned it a bit. So now we're looking down on this. So for our outermost integral, which we'll make with respect to x, we'll put dy in the middle. We'll use our top view to see what the limits should be in x and y. What is the extent of x? So x is our outermost integral, so we need constant limits. We need to find out what is the smallest and largest x values that are included in this solid. Keeping in mind that here we have a circle of radius 2. So what is the extent of x?
Plus or minus 2.
Yeah. So minus 2 to 2. So we see that here we have x equals minus 2. I'm putting negative up here just for consistency with this picture. So I'm taking this and just turning it a little bit. So we have positive x running down this way and negative x running this way. So the solid is entirely contained between these planes, x equals minus 2 and x equals 2. So those are our limits in x. Now we have one set of limits left for y. So what should y be for any particular x between here and here?
It could also be 2 and negative 2, couldn't it?
Well, if we wanted y to be our outermost, we could do that. But now, if you do x from minus 2 to 2 and y from minus 2 to 2, you don't get a half circle, you get a rectangle.
Okay.
So the limits in y are going to depend on x, because for this x, you go from here to here. For this x, you go from here to here. So how do you cover that half of the circle?
Well, you always start at here, so that's going to be 0.
Wait, what?
Like when you were saying you go from here to here.
Oh, yeah. Yeah, so your lower limit is y equals 0. All right. And starting from y equals 0, how far do we go in terms of x? It has to be in terms of x.
The square root of 4 minus y squared?
Yes. Square root of, no, not y squared.
X squared?
Yes, 4 minus x squared.
But didn't you say you wanted it?
I said in terms of x.
In terms of x, not
Yeah.
x equals. All right.
Yeah. All right, so this is one set of limits that would work. We could have swapped these two because well, actually that'd be more of a pain. You could do it. You could have y go from 0 to 2. All right. Let's go ahead and fill this in. So you can see the different ways of doing this. So z is still our innermost integral. I'm not going to change that. We'll put x in the middle, and y is our outermost integral. So if we wanted to do limits in y, what is the extent of this in terms of y? It goes from y equals what to y equals what? Constants. Not this time.
0 to 2.
0 to 2. We start here and we go here because we're only taking this portion. So it's a little different. So y goes from 0 to 2. And now, for each y, what is the extent of the solid in terms of y? Well, so you're going from this x to this x for each y between 0 and 2. Square root of 4 minus y squared, but, well, there are two limits. What are the two limits? Be careful.
Positive and then negative.
Positive, yeah, you go from negative to positive.
Okay.
Yeah, so minus square root of 4 minus y squared up to positive square root of 4 minus y squared.
Yeah, but we don't want to do that.
Let's do that.
Right. Yeah, it's nicer to have more constant limits in there. You could use symmetry, like even functions, to double it up, but yeah. All right.
So we could do that though. We could say from 0 to 4 minus y squared, or the square root of 4 minus y squared, and then just multiply the entire integral by 2. Pull that 2 out to the front.
For this integrand, yes, because it's just a constant. Or if the integrand has a nice symmetry to it, if f of minus x yz equals f of x yz, so for symmetry, if it's even in the x variable,
Right.
you could do that.
Okay.
Yeah. If it's antisymmetric, like an odd function,
Right.
0. Trying to understand the solid, how much does your solid extend in terms of these variables? That's the first step towards figuring out the limits. All right. Now, we have limits. Well, we have two sets of limits. Now, let's suppose we're going to actually evaluate this thing. We'll pick this one. So, you can think of this, I guess, kind of like the childhood game of bloody knuckles. When the integral gets too painful for you to continue, then we can stop and consider something else. All right. So, first we're going to do the inner integral, the innermost, with respect to z. So I'll just repeat. What?
My little brother.
Oh, yeah. Okay. All right, so when you do the innermost integral with respect to z, what is that going to give you? Especially because the integrand in this case is simple. So we get z with these limits plugged in, x squared plus y squared up to 4 dy dx. And then, you're just plugging the limits and subtracting them. So you get 4 minus x squared minus y squared dy dx. Okay, one integral down, that wasn't so bad. Now, then we do the next innermost integral of the dy. So what is that going to give us? 4y
Minus y squared.
y minus y cubed over 3 dx. Evaluated these limits, 0 and square root of 4 minus x squared. All right, plugging in 0 won't give you anything. So then you plug in the other limit, square root of 4 minus x squared, and you get integral from minus 2 to 4. Actually, I'm going to simplify this just a little bit, because you can take this part and factor out a y. You get 4 minus x squared times y. So we're going to get 4 minus x squared, square root of 4 minus x squared, minus square root of 4 minus x squared cubed over 3 dx. Starting to get a little uglier. So now we combine this. This is 4 minus x squared to the 3/2 power. And we can rewrite this as 4 minus x squared to the 3/2 power as well. We can actually combine these into one fraction. All right. So we get 4 minus x squared to the 3/2 times 1 minus a third. So we get a 2/3 out here. All right. So we've gotten to this point. Now what?
You use your cylindrical
You peeked ahead, didn't you? If you were not allowed to do that, or it didn't occur to you to do that, how would we go about evaluating this? Trig substitution. Yeah. What would the appropriate trig substitution be in this case? There's certain expressions you look for, square root of various forms, and that tells you which trig function you're going to use. 2 sine theta. All right, so a quick review. If you have something like this, a squared minus x squared, use x as a sine theta. A squared plus x squared, use x equals tangent. And finally, we flip the sign in this one, and secant. So those are the 3 you use for those situations. You never know if you might need them, like on a final exam or something.
That's not cool.
You have like 8 weeks warning.
Yeah.
Was that from Cal 2?
Yeah, it should have been.
Okay.
Oh,
Just over
Yeah.
2 years.
Okay, I'll put them on a formula sheet or something. All right. Okay, so we use x equals 2 sine theta. So in that case, dx is 2 cosine theta d theta, and the square root of 4 minus x squared is 2 cosine theta. So now you can rewrite this whole thing in terms of theta. So what we're going to get is, well, we have this cubed. All right, we have a 2/3 out front. I'm not going to bother with the limits right now. So we're going to have 2 cosine theta whole thing cubed. And then we have dx is 2 cosine theta.